Hello friends, welcome to my channel. Let's have a look at problem 1749, maximum absolute sum of any subarray. In this video, we're going to share some treatments with dynamic programming, or we can see just linear scan and check. First, I'll read through the statement to digest the requirements, and then we do a simple analysis, and finally we share the two formats of codes. First, let's look at the statement. We are given an integer array called nums. The absolute sum of a subarray is given by the sum and the take absolute value. So we are required to return the maximum absolute sum of any possibly empty subarray of nums. So here are two examples. In example 1, the output is 5. So the corresponding subarray is nothing but 2, 3 right here. And in example 2, so the maximum absolute value for a subarray is -5, 1, and -4. So the sum is -8, so the absolute value is 8. So the constraints for this problem are the following. First, the list is not empty because the length is bounded below by 1. And the length has an upper bound, that is 10 to the power 5. So this number actually gives us a upper bound for the problem size. And secondly, it tells us the assumption on the elements range. So here what we want to emphasize is that the number here can be negative. So actually if all the numbers are positive, we just need to return the whole sum, right? That will dramatically simplify the problem. So with that said, let's look at the treatment and the code we are going to share. So the treatment is basically based on dynamic programming. So this is in the larger horizon. All we can see is we just need to do a linear scan and do a check. So here we are going to share two solution formats. The first solution format is what we think when we see the problem. And the second one, actually, it makes connections with a well-known algorithm. It's called the Condensed Algorithm, and essentially also dynamic programming. So let's look at the first solution format. So at each position I, so we can get the possible smallest, largest values ending there. The reason is that the absolute value, the maximum absolute value, is either corresponding to the largest sum or the smallest one. So here, the reason we consider these cases is due to the fact that the elements in the list can be negative. So we'll call them little m and capital M. So at next index I plus 1, we want to update this m, little m, and capital M. So actually they can be updated by considering the three numbers below. So little m plus nums I plus 1, capital M plus num I plus 1, and nums I plus 1 itself. So in other words, so this what we are going to do is to record the corresponding largest and smallest possible numbers in or subarray sums ending at a specific index. So here the new little m and capital M will be the mean and max of the above three possibilities respectively. So in the process, we could update the result state by considering the max of the previous state result state and the absolute value of little m and capital M, right? So that's the first solution format. Let's first finish this solution format, then let's look at the condensed algorithm. So first, I'm going to make some preparations. So this is actually very routine. So first, I'm going to get the length of nums. So this is just for convenience of iteration. Next, I'm going to iterate the result and little m and capital M. So because the nums array has length at least 1, so we can use the first element. So the result, because we want to take absolute values, so it's initialized as absolute value of the first element in the list. And then little m will be nums 0, and the capital M will also be nums 0. So this is the initialization. So next, we're going to do the iteration, right? So for the iteration, so we just needed to do starting from index 1, right? That is range 1 and ending at n-1, right? So we write n here. So then we're going to consider three possible numbers, right? I'll put it in the list. So one is little m plus nums I, and the other is capital M plus nums I, and the third one is nums I itself, right? Because we want to record the largest and the smallest subarray sums ending at the index I. So we need to consider nums I. So with that said, the little m and the capital M will be the min of temp and max of temp. So in between, we can update the result state. The result will be max of the previous state and the absolute value of little m and absolute value of capital M, right? So it's possible that the absolute value of little m is larger than that of capital M, because if little m is very negative, right? So it has a larger absolute value. So that's why we consider this absolute value and this absolute value, right? So afterwards, so we're ready to do the return. So return the result. So this is the one format of solution corresponding to our first thought. Let's do a check. It passes example 2. Now let's look at generic case. It passes all the cases. So now let's make a connection with the condensed algorithm. Actually, this solution format here is a space optimized condensed algorithm, but for presentation purpose, let me write another one. So I'm going to verbosely using condensed algorithm. First, let's look at the intuition. So for the second solution format, we could use condensed algorithm to find max or min at each index. So essentially the same thought, not thought is the same thought, not stuff. But this bears a name, so seems cool. So note that the original condensed algorithm is for finding maximum subarray sum, but we could easily adapt it for doing finding minimal subarray sum. So this is no difficulty at all. So the maximal absolute value must be the maximum of the 2 among all ending indices, right? So here actually we can do a remark before we write the code. So condensed algorithm can be used in many different cases. So we have practiced a number of use cases for directly using a condensed algorithm or using condensed algorithm several times for certain problems in leetcode. Please check out our channel for other uses and practices. So now let's look at the second solution format. So we're going to use condensed algorithm. So for this, I'm going to write with some redundancy so that we can understand the result, the things better. First, preparation. So I'm going to use DP table just for the clarity. So essentially, I do not need to use that. So here, let's use n is the length of nums, and then I'm going to compute the max and min of at each index using condensed algorithm. So I'm going to call it Kadane max. That's going to be 0 times n. So length n list Kadane min as 0 times m, right? So now we want to make some initialization. Kadane max at 0 is nothing but nums 0. So Kadane min 0 is nothing but nums 0, right? So the result, I'm also going to initialize a result. The result will be absolute value of nums 0, right? So this finishes the preparation step. So next, I'm going to do the iteration. So we can call it DP update. So we are going to start from index 1, right? So 1 to n. So in some sense, this version is a decomposed version of the first version we presented. So then we're going to do condense max I. It's going to be the max of condense max and I minus 1, right? then plus this nums I, right, and then compare with nums I itself, right. So Kadane min I, which is going to be Kadane min at the previous index, then plus nums I, and then compare with nums I itself, right. So then we can update the result state. So the result will be the max of the previous result, and then the absolute value can be coming from the max or min at each index. So we're going to use absolute value Kadane max I, and ABS Kadane min at index I. So that's it. So afterwards, so we're ready to return the result. So this actually decomposes, or is a detailed version of the first solution format. Let's do a check. Yeah, it passes example 2. So now let's look at the generic case. Yeah, it passes all the cases. I guess that's it for this specific problem. So I would say, so the solutions or solution formats here follow the idea of dynamic programming in general, but the problem context here is very simple. So we can see you need to use a linear scan and check. So if we want to put it with a name for some algorithm, so here we are using condensed algorithm. So with that said, I guess that's about it for this video. Thank you.